Sample problem 13.9 kind of is the last problem that we're going to work on from chapter 13, and I love this problem for many reasons. One is I often say a picture is worth 1,000 words, and so I love having these pictures here because it requires us to think about some things conceptually, make sure that we understand them in this chapter on mixtures. And then secondary to that is the fact that it does still allow us to apply some of this knowledge and do some of the calculations that are related to this chapter with regards to colligative properties. Okay, so this problem tells us that we have a 0.952 gram sample of magnesium chloride, and it dissolves in 100 grams of water in a flask. And so the first problem is very qualitative, and it just asks us to think about which of these molecular scenes, and this is what these problems refer to. They say using molecular scenes to answer problems. Which of these scenes depicts the solution best? And so we see three flasks that are here, and our little key reminds us over here that every green sphere that we see is a chloride ion, and every magnesium ion is represented by a smaller blue sphere. And so we need to look at these and ask which one of these depicts the solution best. So anytime you have to look at something like this, first look at this and ask the question, well, what's different between these? Well, I can look at C and I can see that C still has the blue spheres associated with the green sphere, which means that it's indicating that we're supposed to have this salt still together. Well, because they tell us that this solution, we have a solution where the magnesium chloride dissolves, I can rule out C for that reason, because this solution is not dissolved. But secondary to that, I can actually look here and look at the makeup of one of these, and this tells us that we have 2 magnesium ions for every 1 chloride ion. And I know that that's not going to be the case for magnesium chloride. Magnesium is a divalent cation, and chloride is a monovalent anion, meaning that the salt that it came from was MgCl2, not Mg2Cl. So for 2 reasons, we can rule out C as being a scene that depicts the solution best. Okay, so looking at the differences between A and B then, the main difference is that there is a 2-to-1 ratio between the chloride and the magnesium here. So solution A has a 2-to-1 ratio between chloride and magnesium, whereas solution B also has a 2-to-1 ratio, but now that 2-to-1 ratio is twice as many magnesium ions as we have chloride ions. And for the reason that we just talked about over here, we know that when magnesium chloride dissolves in solution, because it's a divalent cation, there's going to be half as many as we have monovalent chloride anions. So in that case, we can rule out B, and A is the correct answer. So that is the scene which best depicts the solution. Okay, moving on. Problem B asks us to think, B of this problem asks us to think about a little bit more quantitative aspects of this. It asks, what is the amount in moles represented by each green sphere? So we're going to work forward from this solution, assuming that that's the best solution, and think about what each green sphere represents. Okay, so it's a little bit weird to think about this because we have a little picture here and we actually have some information. But what we need to do is we need to figure out how many moles of magnesium chloride we have here, translate that to how many moles of chloride we have, and then divide by 8 because we have 8 of these spheres. And that will tell us what each green sphere represents. So hopefully that makes sense. We're going to walk through it here. All right, we know that we have 0.952 grams of magnesium chloride. And if we want to figure out how many moles that is, we can use the molar mass of magnesium chloride for that. So 1 mole of magnesium chloride is 95.21 grams. And that tells us that we have 0.0100 moles of magnesium chloride that we dissolve in solution. Okay. This question asks, what is represented by each green sphere? Since each green sphere represents a chloride ion, we need to carry this calculation one step further and say that for every 1 mole of magnesium chloride that we have 2 moles of chloride ion. And again, the chloride ions are what the green spheres are. So we need to figure that out. So this tells us that we're going to have 0.0200 moles of chloride ion in solution. And since this problem asks us what's the amount represented by each green sphere, this is the total amount of chloride in solution, which is represented by 8 spheres. So what we really need to do is we need to take this 0.0200 moles of chloride ion in solution and divide by 8 spheres to get that there's 2.50 times 10 to the minus third moles of chloride ion represented by each green sphere. So that was kind of a different kind of problem, but again, a kind of problem that you might see on a quiz or exam where you have a picture that you have to translate some way into a calculation. Okay, the last part of this problem is kind of more traditional in terms of what we've seen with our previous 2 problems. We want to calculate what the freezing point is at 1 atmosphere. And importantly with this one, it tells us to assume that the solution is ideal. And what that means is, remember that we have a salt here. And that salt means that 1 mole of salt, when it dissociates, is going to create more than 1 mole of particles. And how many particles it makes is dependent on what the salt is. So let's just kind of examine this salt here and see what we have. So our salt, again, is magnesium chloride. And when we dissolve and thus dissociate it in water, we're going to get 1 mole of magnesium ions and 2 moles of chloride ions, which means we get 3 moles total of particles. What that means is that our I value is going to be equal to 3 in an ideal situation. And we need to take that into account when we do our calculation here. Okay, so I'm going to flip to a new piece of paper here to finish this problem out. Remember, change in the freezing point depression, is going to be equal to I times Kf times the molality here. Kf, again, would have to be provided for you, and since we have an aqueous solution, it's 1.86 degrees C per mole. We're going to have to figure out the molality of the solution, and we just figured out previously that the I is going to be 3 for a magnesium chloride solution. So molality is equal to the mole of solute per kilogram of solvent. Well, we just figured out that we have 0.01 moles of magnesium chloride and 0.100 kilograms of water is information that's given to us. They told us that we dissolved this salt in 100 grams of water in a flask. So the molality of the solution is 0.100 molal. Plugging this into our equation, delta TF equals 3 times 1.86 degrees C per mole times 0.100 molal, and that's 0.558 degrees C. Now this problem, remember, asks us what is the freezing point, right? This problem asks not what the freezing point depression is, what is the freezing point? So that means that we need to figure out what the new freezing point is. To figure that out, we take the normal freezing point, which is 0 degrees C, and we need to subtract off what the freezing point depression is, 0.558 degrees C. So the new freezing point is negative 0.558 degrees C. Just putting this in perspective with sample problem 13.7 that we just did, in this case, we have something that's 3 times more effective at depressing the freezing point than, for example, if we had used ethylene glycol, which was the substance used in sample problem 13.7.